So Dr. Gurkan Solmaz is a senior researcher at the NEC Labs Europe in Germany. His interests are in mobile computing, AI, machine learning, and edge computing for novel IoT and applications to smart cities and smart mobility. So Gurkan, I invite you to give the next talk. So please go ahead. So I'm sorry, Gurkan. The topic that Gurkan is going to talk on is multimodal data analytics at the edge. Please go ahead, Gurkan.
Just a second, please. I need to share my screen. I need to swap the. Do you see my slides now?
Yes, yes, Gurkan, please go ahead.
Hi, thank you very much for the invitation. My name is Gurkan Solmaz, and today my title of my topic is the talk is multimodal data analytics at edge. So here is a short outline. I would like to first define what I mean by IoT multimodal data analytics systems. And then the talk will include 3 different recent studies, 2 related to crowd mobility analytics, and 1 is related to automated driving. So here is, oh, sorry, I need to get rid of, I think this, yes. So before this, I had another slide. Yes. So here is what I mean by multimodal data analytics. I talk about various sources, data sources, for instance, various sensor data, can be cameras, can be Bluetooth, wireless sensors, or other sensors on the vehicles, or smartphone sensors. And also open data can be data that are reachable from the web or other data sources. And here we want to analyze these various data sources as multimodal data sources using IoT, which includes, of course, edge and cloud. So these systems also have embedded machine learning. So you can have also like feeding different models. For instance, if you have a domain knowledge or physical model, you can also feed to the system. And the idea is applying this to different domains. For situation classification, for instance, for awareness in smart cities, smart mobility, or other industries. So by IoT sensors, I mean the wireless sensors, ground deployment drones, or remote sensing, different remote sensing applications. And so, and the general goal again is to recognize activities and behavioral insights and create behavioral insights. So understanding crowd mobility in smart cities is a key enabler for various reasons. For instance, it can be useful for public safety, can be useful for optimizing transportation. And also, for instance, today we have this epidemics problem. So it could be also useful for epidemics. And on the other hand, there is a really a big issue for knowing estimating crowds, especially without violating the privacy, for instance. So, and if you use only wireless sensors, for instance, then you have more inaccuracy in your crowd estimation due to various environmental dynamics. And you can have, for instance, crowd overestimation, which is when you have a range of your wireless sensor, which is larger than the point of interest, or you can have various vehicles passing by. Or you can have also the crowd underestimation problem using wireless, because then you may have, for instance, people in a hurry passing by, then you may not able to understand that there's any wireless activity from those people. So here on the left side, you see some illustration of the deployment in a train station in Wellington, New Zealand, where we had, for instance, Wi-Fi sniffers, wireless scanners, and also stereo cameras, which are able to just count the number of people passing by the gates in the train platforms, as opposed to, for instance, recognizing face or other. So here on the right side, you see the crowd overestimation and underestimation problems I just mentioned as illustrated here. So we had an approach which was based on using this idea of calibration choke point, where you have both of these sensor modalities. One was this, again, the stereo camera, which gives you the people count in a relatively high accuracy. And the other was the Wi-Fi sniffer, which provides you some general estimation, but mostly it's because of the environmental dynamics. I just mentioned a couple of examples. Because of this, the estimation is mostly not true, and there are lots of noise in the wireless data. That's why in the calibration choke point, we had this idea of having two of them together and kind of understanding this correlation between these two modalities. And then considering you have maybe wireless activity you can detect in a larger area, but in a camera you have really limited range. And the idea is, what if we had some area which we had only wireless scanners? Can we use this learned correlation on also these areas to calibrate the results for the wireless measurement? So we had a prototype system which we first implemented in a Raspberry Pi, as you see on the left side, which had the Wi-Fi antenna and other components. And on the right side, you see a more commercial device, which is NEC Kite device, which is a sensor platform for smart cities. This was considered for more like larger outdoor deployments. So on the left and right, you see indoor and outdoor deployments, which took place in New Zealand in collaboration with NEC New Zealand. On the left, you see the Wellington train station. I also mentioned the illustration for this. You see here the gates to the platforms, and you have actually here like 4 gates, for instance, and you had these wireless scanners. And on the right side, you see another New Zealand city, Christchurch, and there was an open area shopping mall. In this area, we had some outdoor deployments, again, using NEC Kite devices and also the stereo cameras. So we proposed 2 different algorithms. I'm not gonna go into the detail of these algorithms, but you can find it in the paper. But the idea was basically applying this correlation using these 2 different algorithms, which can kind of calibrate dynamically. And we noticed that these wireless measurements, the modality of the data using wireless, normally it's noisy, as you know. It was mainly using basically not even RSSI, and some problems. For some other problems we use RSSI. Then, but the good news is we could actually calibrate with a very high accuracy compared to the Wi-Fi only approaches. We also noticed both of these overestimation and underestimation problems may appear in different non-peak hours or peak hours in the, let's say, in a train station. And these algorithms were able to handle these situations. So the second problem I would like to mention is a group inference. This is more even extracting more patterns from the crowds, again, using wireless traces from the mobile devices mainly. And the idea was, can we detect static or moving people groups? And applications of this problem would be also quite wide. For instance, you can use it for managing of events, smart retail evacuation modeling, social isolation detection. And today's, for instance, you can also consider it using for understanding social distancing behaviors. So you have, let's say, an area where there are various people, and you have some Wi-Fi wireless scanners deployed in the area. In this case, we consider Bluetooth scanners. And can we extract the groups from each other, understand what are the sizes of each group, and so on. So there are various technical challenges, and also there are existing solutions, different solutions, which we mentioned in the paper. And they are, of course, they have various limitations also. And our question was, considering all these limitations, can we infer groups in a fine-grained way with minimal or no training and using only wireless traces? So this was the question. And here on the top, you see some example data. Example data coming from a Bluetooth scanners. The first one, second one, and the third scanner, 3 different scanners at the same time. You see how they have very different dynamics actually in the measurement. So other than this, I mean, why this happens is also partly because it's a well-known phenomenon that normally you can use, for instance, the signal strength should indicate the distance between a sender and a receiver, but there are many environmental conditions. Because of that, mostly this data is not reliable. So we found out two key problems here. One was the data was sparse and also it was noisy. And the other problem was, even if you collect all this data, considering the sparsity and noise, how can you combine this continuous time series data from any number of scanner and devices? So for that, we proposed an algorithm. So this is our approach actually. We consider kind of a step-by-step approach from left to right. And the first step was scanning using multiple observer. And again, the number of observer was not defined, but we assume there are multiple observers. And the second step was pre-processing, which considers sampling and normalization. The third step was centralized and decentralized computing, in which we proposed two different algorithms. And again, I'm not going to go into the detail, but you may find on the paper. And the last phase, we had the group detection, where we consider, for instance, graph clustering algorithms and long-term linkage detection, which means understanding the long-term linkages between the people in the groups. So here is our experimental setup. On the left, you see here a gateway, Bluetooth beacons, and also Raspberry Pi devices, which has also a Bluetooth, which served as Bluetooth scanners. And here is the setup in the lab environment. You see the distance between the scanners were about the 10 meter, and they were all connected to the same gateway, and we had a backend server also. So we had conducted controlled experiments through short data collection campaigns. For instance, 27 different scenarios we tested in the lab, and each of them were only about 10-minute duration. Other than that, we had a longer data collection for about a month in a more real-world scenario. And we also consider different other algorithms applying to this multimodal data coming from Bluetooth. And also we consider different metrics for accuracy. So here is the some results for the office scenario, which we had controlled experiment and also real world scenario. We noticed in both cases we had very good accuracy, up to almost 100% accuracy. But in the real world, it's up to a bit more than 80%. So we also wanted to see, even if this group inference is accurate, what should be the distance between different groups so that this grouping approach works. So we considered, again, we proposed before centralized and decentralized algorithms. So we tested for both of them. And we noticed as long as you have different groups, which about 4 meter interdistance with each other, then the grouping approach works with a really quite good accuracy, that this grouping approach can differentiate these groups. But when you get the groups get closer and also consistently, so then the problems arise, of course, because if you have, for instance, 2 meters or 1 meter distance, and this is consistent, then this approach cannot differentiate these groups. So here is some example visualization we had for the group mobility inside dashboard. You had the number of groups, number of people, and also the groups, formed groups listed on the table, which you can see on a live web interface. And also the consideration for the long-term linkage, and as a result was, can we have a social network of people based on their mobility? And based on that, can we understand the socially isolated people? So this one, this study is about the automated driving, and the idea is, can we apply this multimodal data analytics for automated driving? So here we have mainly an automated vehicle, which has an in-vehicle IoT platform, edge IoT platform, and we consider doing the analytics on this platform basically. And there are many data sources here also. Data sources can be coming from the vehicle itself, which have, for instance, different vehicle sensors like cameras, radar, lidar, other sensors. Can be people using smartphones or other wearable devices, for instance, on the street. And you can have other data sources, for instance, from the public transport, traffic operators, and others. So why this is important is because the safety is especially a very key challenge here. Considering the Uber accident, for instance, in 2018, it really had a really big impact on the industry, for especially considering the automated driving scenario. And this accident showed that actually both the driver can easily fail, as shown in the video, for instance, and also sensors can easily fail too. So these two are actually a reality. That's whatever you do, these two will kind of fail in certain situations. So, but on the other hand, we have various opportunities here. For instance, for mobile sensing, considering mobile sensing and vast amount of sensors available, and in roadside units also, not only on the vehicle, but also on the roadside unit. And also there is way of different vehicles cooperating through vehicle-to-vehicle communications or vehicle-to-X communication, for instance, vehicle to the roadside unit. And other than that, we have also 5G technologies coming, as well as we have the opportunities for edge computing. Again, you can do your analytics on the vehicle, but also on the roadside unit and so on. So the idea was, can we support the safety through IoT? And we identified two problems here, actually. One was the pedestrian detection, detecting the pedestrian accurately. The other was pedestrian intention prediction. So I will mention the second one here, which is about, you have, for instance, this trajectory of a pedestrian, and this data coming from a smartphone, let's say, for the user. And you have actually different GPS trajectories. The question is, like, at a given point, given the old measurements, can you predict the next steps, the movement steps of the pedestrian using machine learning? There are many things you can use, many modalities of data. For instance, from smartphone, you can have accelerometer, you can have, for instance, speed, GPS, gyroscope, and other sensors too. Of course, you can have other sensors except on smartphone too, but in this study, we only used the smartphone sensors, and we mainly focus on the GPS trajectories for estimating or predicting the movement steps of the pedestrians. So for this study, we had conducted experiments jointly with the Technical University of Eindhoven in Netherlands. And in the campus, we had this automated driving scenario, test for automated driving scenarios. And the TUE campus has about 2-kilometer road network, and the speed limit of the vehicle was only 15 kilometers per hour. And this automated driving was custom built by the group in the TUE. And it was on almost all of the tests, or most tests, it was mainly automated. So the vehicle was uncontrolled, whereas we had predefined pedestrian movements. So the pedestrian movement was controlled in our case, but the vehicle movement was uncontrolled. With this logic, we conducted various experiments in the campus. So here is, you see an example. My friend here carrying a bag of various smartphones and ITS G5 devices. And in the vehicle, we had vehicle sensors such as camera, lidar, and also here you see the controlled pedestrian trajectory. In this scenario, for instance, pedestrian is supposed to cross the road. So the ITS G5 device directly connected to the in-vehicle IoT platform. And we had actually like multiple of them in order to kind of cross-check. And also we had many, for instance, smartphone, tablet, or other devices. And these devices, such as smartphone, they were going through the IoT platform on the cloud. So they were connected to cloud through 4G, using cellular 4G. And in the in-vehicle IoT platform, we had the robot operating system, which was collecting all the data. Then we had the analytics. So here on the bottom, you see the visualization from our own visualization from this scenario, for instance, when the pedestrian passed here is the trajectory for the pedestrian, and here is the trajectory for the automated vehicle. We here evaluate the intention prediction. But before going to the accuracy of intention prediction, we first wanted to see, especially from the smartphones or using 4G and cloud IoT platforms, what was the message delay for the data to arrive to the robot operating system in the vehicle. So this is a little bit hard to evaluate because there are many different components. For instance, in the smartphone, but from smartphone, it goes to the cloud, and in the cloud, there are various components. And from cloud, it comes to the vehicle, and in vehicle, there's a gateway, then the gateway passes to the robot operating system. So as you see, these components also came from different groups. So that's why we weren't sure how much delay we will have. So here you see, as you see, it was most of the time about, on average, let's say 0.6 seconds delay. And this was from our observation. The message arriving from smartphone to the vehicle was about 0.6. And this was mainly because, in my opinion, and also our observations, it was mainly because of the implementation issues. For instance, the implementation has always some problems, especially if you are using prototypes. And that's why. So this message delay can be, of course, shortened. On the other hand, it gives us a good motivation to use more edge computing, for instance, because if you use edge computing, you don't need to go through 4G, 5G, or from, for instance, in the cloud platform or others. You can actually do analytics directly from data, can come from pedestrian to the vehicle, then the vehicle can analyze the data. So we used Ludwig and TensorFlow to train and validate our machine learning model. And we consider different consecutive data points. And here you see this prediction, like the first step of the pedestrian, second step, third step, and so on. As you see, when the steps get further, the prediction is worse, of course, because you try to estimate the fifth movement step of the pedestrian here. And we also considered for different scenario, one I showed the straight walk scenario, the other one was, for instance, coming to the street and turning left instead of crossing the street, turning right. And this is the average. We found that the walking straight has the best accuracy, as you might expect. But the good thing is, without too much training or too much data collection, we could actually decrease the error. What I mean by data collection is using GPS trajectories, but also you could use other sensor data too, which would help this accuracy. And also you might have longer measurements even. But the good thing is we still had a decrease in the error for the intention movement prediction. So to conclude this study, we think the learning from IoT would improve the safety of autonomous driving or automated driving. And these type of systems on cloud and edge can complement existing safety solutions. Especially edge computing would greatly enhance the safety of the pedestrians. And here we consider two key problems. One was the pedestrian detection. The other one was intention prediction, which I mentioned. And other than these two key problems, we encountered another key problem during our test, which was the hybrid automated vehicle. We had run out of gas. So here on the left, you see myself trying to solve this old problem manually. To conclude my presentation, I would like to give some takeaways. First is cloud edge systems would be really useful for multimodal data analytics in real-world scenarios, various real-world scenarios. Here I gave only some simple examples here. And there is a definite need for edge analytics algorithms. For instance, in the group-in study, we had some decentralized algorithm, but there could be many other ways of doing it for group inference, but also for other problems. And we see there is a lot of opening here in terms of we don't have these algorithms, especially for machine learning. But the good news is there are now lots of studies arise for federated machine learning, for instance. But federated machine learning is kind of a limited version of more general distributed machine learning, maybe. So there is still lots of things to do here. And applications to the smart domains. Once you have such cloud edge systems, which are working really good accuracy and also for other metrics, then you can apply in different domains such as smart cities mobilities, smart mobility, as I showed in this presentation, but also you can have smart agriculture, smart industry, or other domains. So lastly, I would like to say that there are various key performance indicators and metrics in the real world scenarios. For instance, when we look at the machine learning studies, recently they are mainly focused on accuracy aspects. While federated learning is already focusing on scalability too. Here we consider scalability on the time and space domains. But other than that, you can have, of course, energy efficiency, security, privacy, and many other metrics. And these metrics become more important, especially considering edge analytics scenarios or IoT scenarios in the real deployments. Thank you very much. It was the end of my presentation. If there is any question, I would like to answer them. Thank you.
Thank you, Flavio, for the excellent presentation. So I think there are, we have time to take one question. I'll just read out the question. And see, the question is, how do you decide when to go for edge analytics given the data under consideration and the underlying algorithm?
That's a good question. I think it's, of course, very related to data, but it can be also related to other concerns. And here I mentioned these KPIs. I think they are very relevant for this question. If you have, for instance, if you want to scale your system, if you want to have a really large scale data analytics, like large scale crowd mobility analytics in the whole smart city, then you will want to not send all the data to cloud, but do most of the task maybe on the edge. You can also think it for energy efficiency, different communication problems, as well as privacy is really key, especially in smart cities or these some of the applications I showed also use data from people. That's why you don't want to send the data from people maybe always to the cloud. So that would be really interesting to explore actually. But the question is like, then, okay, you need to do it, use edge analytics and make it scalable, energy efficient, and so on. But is there an algorithm for that, for the given problem? Is there really open, I think.
Thank you, Gurkan. So thanks a lot for your talk.